Because now I'm going in the direction of the elemental, of the fundamental, which is this. What is the elemental in this drawing? It is the coexistence of say, tributaries with a mother channel, or in the other direction, coexistence of a mother with, in this case, two daughters. These are words from hydrology. I'm not making fun of anybody. All right? And this is how the story begins. What is the origin of this configuration that's like the, say, molecule in a bigger blob of material? And, you know me, it must be the Constructal law, meaning that configuration is predictable. And I teach it as a relatively simple piece of homework this way. You have a drawing of this size called A. And on A, there are actually three tubes, three channels. Here they are. In other words, I'm drawing a T-shaped structure. The cross-section of all the tubes is round. The mother tube has the length L1 and diameter D1. And the, let's call them two branches or two tributaries, have the same length called L2 and diameter D2. And the rectangle is your page, the page on which you make the drawing, or the field of vision in front of your eyes, or, believe it or not, the field of vision you have in your imagination, because you spend most of your time imagining, not looking at things. Think about that. This is what you're doing. And it looks not exactly like this. I already made the point that your field of vision is aligned this way, like the screen of the cinema. But it is an area called A. And what do you need to know in order to make the drawing? The drawing could be big or small, but what must you know in order to make sure that the drawing tells you or the viewer that there is one big channel that is connected to or owes its existence to two tributaries that are smaller? Did any of you study art? Art. A-R-T. Nobody. You're all aspiring to become engineers? I mean, think about how nonsensical that is, to become an engineer without knowing how to make a drawing. No, really, I'm putting my finger on some of your missing organs. That's kind of funny. Cannot touch what's missing. But the point is that in the university, you come to learn things, but you also come to discover things you don't know. And yes, it pays to become interested in for example, why some of the most famous engineers were very good at art, such as Leonardo da Vinci, very good example. Okay, to make this drawing, this particular one, I intuitively, I assumed that I knew proportions. I knew that D1 over D2 has to be bigger than 1, meaning I know because I was not born yesterday. And I knew that the other lengths, meaning L1 over L2, the way I drew them, they should be of a comparable size. But to make a drawing, you need proportions. Try to make a drawing of your classmate's face. If you don't know proportions, then the drawing is going to end up showing that your classmate doesn't look like your drawing, because the classmate doesn't have that big nose that you put on the page. You see? So proportions. Proportions are the ingredients in drawing, and the name for drawing is design. So I'm hinting already that to get to design, you need proportions. These proportions are up to you, knowledgeable or not knowledgeable. But even if you know them, you have the freedom to use the better ones as opposed to the bad guesses. In other words, you'll see very soon that these ratios, the proportions, are the degrees of freedom to the person, or in the mind of the person who makes the drawing. How many? All right. Now that's just seat of the pants thinking. Now we are, students at Duke. We know how to do this much better. And we begin with with the more basic facts. I already mentioned one, and one is that by the way, Ahmad, are you really catching everything up to here?
Yes.
You sure? All right. In that case, I will spread myself. So the way to proceed is to think about the size of the drawing. I mentioned one measure of size is the size of the page. You can think of that as the external size, which happens to be what? 2, L2, L1. In what follows, because I'm not here to split hairs, I'll recognize only that A is proportional to the product. So that's the external size. The other size that's sketched here is the volume, the flow volume. For example, the volume of the blood that flows through this bifurcation. So flow volume happens to be pi over 4 d1 squared L1 plus 2, because you have 2 branches, and then pi over 4 d2 squared L2, which means that this so-called internal volume is proportional to d1 squared L1 plus 2 d2 squared L2. So we have two measures of size in this particular drawing. And how many variables, how many lines, the dimensions of which you could change on this particular drawing. You can count the symbols. There are 4 dimensions. You can call them 4 variables. You can count them. You see, I actually wrote them here. And are they all independent? No, yeah, no, okay, so your yes means no. Good play. I like that. Yeah. And some of them are not independent, and they're not independent because of the two measures of size that have been specified here. In the mathematics, people talk about the variables and the constraints. So 4 variables minus 2 constraints leave 2 independent variables. Only 2. And which 2 of these 4, it's up to you. I like to work with dimensionless variables, such as ratios. And this is why intuitively I was already convinced that the degrees of freedom could be these 2 in order for me to make the drawing. So the bottom line is correct here, 2 degrees of freedom. And next comes the exercise, at the end of which you'll see how easy it is to figure them out. You see? Any questions? You see the beginning? And this is where the story begins. By the way, yes, you could catch fish with this kind of thing. For example, with the trident of Neptune, you know, the god of the seas. Trident means 3 teeth. That's a way to spear fish with giving yourself 3 chances, right? Do you know what I'm talking about? You've seen Trident. It's also the name of a submarine. I mean, there's lots of uses to that old image. Okay. But
by figuring out the degrees of freedom, you mean maximizing flow?
Well, yes, yeah. By behaving intelligently, which is that you'd like to discover access. In this case, access to what flows through this drawing, because this drawing is alive. There is a m dot that enters and exits. That's half of the m dot, and that's the other half. The T. This is a T design. The letter T is the simplest tree. Get it? Yeah. The cheapest. Because when you are at the start of the road, try the simplest first. A pressure difference must be applied from the left to the right. And this pressure difference, if you think about it, is between this location and these 2, where the pressure is 0. And the delta P shown here is the sum of 2 pressure drops. One is along the L1 duct. I'll call it delta P1. And the other one is along either of these 2 branches, called delta P2. And the size of the delta P, you can regenerate this formula easily if you remember only one, which is the delta P in general is equal to the friction factor 4L over D. This is the hydraulic diameter, 1/2 over rho U squared. We've been through this song and dance before. We start again with the simplest, which is Poiseuille flow. which means fully developed laminar, and in a round tube called D1 or 2. And in this particular case, again, I'm repeating a technique that I put on the blackboard several times already. In this case, the hydraulic diameter is the same as the diameter of the round tube. The friction factor is the same as the Poiseuille number, which for the round tube is 16, divided by the Reynolds number based on D. The Reynolds number based on D is UD over nu. And another substitution is that U is the cross-section average flow velocity, namely m dot over rho pi over 4 d squared. These are the substitutions you make. And then you arrive at a general formula called delta P. In other words, this is an exercise for you if you have not done it already. You arrive at a delta P that's proportional to a constant that is the same for all such flows called Poiseuille. And then the mass flow rate to power 1, the length of the flow path divided by the diameter to power 4. And the constant, if you do this exercise, should turn out to be 128 nu over pi. This is not important, meaning what I just wrote. Important is that capital C is the same for the big tube and the small tube. Delta P1 is obviously C m dot L1 over D1 to the 4th. Delta P2 is C m dot divided by 2, and then L2 over D1 to power, D2 to power 4. And then when you sum them up, as required by this sketch, the penalty to you, this overall pressure drop, is equal to the same constant capital C times m dot, and then a factor that depends on the drawing, the configuration. I call it capital R laminar, which has this formula. It comes from these terms here. It has the L1 over D1 to the 4th plus 1 over 2, L2 D2 to the 4th. This is a function that depends on these 4 dimensions that at first impression were 4 variables, but when in fact they are not all independent, only 2 of them are independent. And you would like to play with these dimensions so that the value of the so-called fully developed laminar flow resistance decreases. That's what that's the direction forward, and that must be done subject to these 2 constraints, and V proportional as I indicated here. And the solution is sorry, the solution out of the mind of the person with experience, meaning Adrian, the easiest is to be executed in 2 steps. 2 steps. Step number 1. Assume or act as if you know the tube lengths. Tube lengths given or assumed. And what vary is this pair, D1 and D2, then D2. And they vary according to the constraint in which these diameters are present, and that is the volume constraint, not the external size constraint. In other words, you want to minimize delta P. Obviously, that's what to minimize this resistance means, is to minimize delta P over m dot. With respect to these two, subject to the internal volume constraint. Let me write this one more time. In other words, the problem statement is right here. This is the problem statement. Analytically, this could be done, again, how should I say, in religious manner. You use the constraint in order to express D2 as a function of D1. And then you substitute that D2 into the formula shown here, or the formula shown here. And you end up with this capital R formula that depends only on D1. And then you take the first derivative with respect to D1, set it equal to 0, and you obtain the D1, and then you go work back and get the D2, and then you report the ratio D1 over D2. That technique was well known in the by now calculus was already in force in the 1700s until Lagrange showed up. You've heard of him, Lagrange. Question goes with this, Lagrange. There are lots of things attributed to him. You know already the joke, so don't start laughing. But he was a major figure in the French Academy of Sciences. Where was he from?
France.
Huh?
France.
But that was the reason why I asked the question, so I could laugh. No, he was not from France. he was from Torino or Turin, the home of Juventus. They play soccer there. Okay. Yeah, in those days, this is now the late 1700s, people hearing their own calling were moving and joining similar types, very few at the time. And back then, the applied mathematics was being born under the protection of the French Academy. And so many of these future applied mathematicians converged on Paris. They came from Italy. Back then, Italy did not exist. They came from Holland and Germany. All these big names you heard about, Leibniz and so on. And he express this procedure at which I was waving my hands in a much easier manner called the method of undetermined coefficients. Which I'm teaching in this course. It is the object of one of the appendices in the textbook. So mathematically, this is a theorem. You can actually prove it, which goes as follows. To seek the extremum of a function, such as this, subject to a constraint, which is the volume constraint in this example, is equivalent to seeking the extremum of a aggregate function, which is a linear combination of the original function and the constraint. In other words, the aggregate function is what I wrote here. And then the other one is the volume constraint that I erased, multiplied by an undetermined coefficient, which in honor of Lagrange is called lambda, because lambda means L in Greek, okay? There are reasons for why people use letters. And then the constraint, volume constraint, is d1 squared L1 plus twice d2 squared L2, in which variable are only the diameters, two of them. And you seek the extremum by performing these two operations. The first derivative with respect to d1 equals 0. The other first derivative with respect to d2 equals 0. And you can do this easily. You see, it's not much of an effort to do this because you learned calculus. And then, so you have two equations from which you eliminate lambda. And the result of that operation in, say, almost without effort, is the ratio d1 over d2. The ratio d1 over d2, meaning the configuration responsible for having minimized the resistance with respect to these two dimensions, subject to one constraint, is 2 to the power 1/3. Yeah?
Does it not impact your answer that you left out the pi coefficient terms for the volume equation?
Oh no, the pi over 4 are eaten up by this lambda.
Okay.
Because lambda times a constant is another lambda, equally undetermined. You see, these mathematicians were really clever. They were clever, acting as if probably it was true. They had a very small supply of ink with which to write. This number, 2 to a small exponent, is actually close to 1. In fact, it's equal to 1.26, meaning it is of order 1, greater than 1, but of order 1. At this point, very important is to make this old drawing one more time with the result on the abscissa and with the wish or the need on the ordinate. And on the ordinate is this resistance which would be better if it were smaller. And on the way to this result, I did not plot how phi depends on this ratio. It depends this way, where the 2 to 1/3 is 1 one design. The performance is one. I'll call it perfection again, or idea, or ideal. And because of the relatively flat bottom of the curve, the good idea attracts a multitude of participants in the design process or in the design room. Every single one claiming correctly a performance that's very close to the ideal. So I made a sketch before. I will sketch those contributors. Here is one of them, neither of whom is as special as the original one that attracted this group. And let's say that their number is n. It is a number that I'll write on the blackboard one more time, as you'll see. Okay? So we know the relative dimension of the two diameters. The next step, it's step number 2. What I had there, and I rewrite it by factoring 1 over d2 to the 4th. And that gives me L1, and then d1 to the 4th, d2 to the 4th, plus 1/2 L2. In other words, I'm restating the problem because I made progress. I executed step 1, and the ratio, meaning the first degree of freedom, is not an unknown anymore. And then this thing is rewritten as, meaning I move everything to the left, 2, d2 to the 4th, the laminar resistance group equals 2 to minus 1/3 L1 plus L2. So this is the so-called function to be minimized, except that what I know is the degree of freedom, which is the proportion, not the value of d2. And I get the value of d2 from the volume constraint, which I erased. Remember, v is equal to pi over 4, and then d1 squared L1 plus twice d2 squared L2. Making the same moves as I've done up there, I factor d2 in front, and then, in other words, I do this d2 squared, and then d1 squared over d2 squared L1 plus 2 L2. And then I obtain the following result, which is that 2v divided by pi d2 squared equals 2 to the power 1/3 L1 plus L2. Kind of amazing. Write these things down because, as you may have noticed, we cannot rely 100% on the video. Sometimes the video is either without sound or without video. So write what you see on the blackboard. Yes?
In the equation right after, like the v equals pi over 4, did you factor in a d1 or a d2 squared?
I have to make sure what you're talking about. So you're talking about this?
The one underneath.
This one?
Yes.
D2, of course. Thank you. Very good. All right, so we've got two statements that follow the discovery of the proportion d1 over d2. You use the constraint one more time by extracting d2 from here and substituting it in here in order to obtain the to distill the figure of merit, in this case, the figure of bad news called flow resistance. And that result is written this way: pi squared over 8 v squared. And then here, this right-hand side, which coincidentally is the same in these two expressions, namely 2 to 1/3 L1 plus L2 to power 3. First observation: if you want a small capital R, it depends on this group in the brackets. I put that on the abscissa. The group at power, meaning the cubic, varies this way. It is increasing monotonically from 0. I'm interested in decreasing it monotonically, so I want to go in this direction, and that means to make this thing smaller and smaller. So to minimize the cube happens in the same direction as minimizing this quantity in the brackets to power 1. So my next moves have to do with minimizing or seeking to minimize this expression subject to the constraint that I did not use before this point, and that is the external size, namely L1, L2 constant. And the technique is the same as before, the one due to Lagrange, which is another aggregate function, psi equals this quantity, and then a new undetermined coefficient called mu, and then the area constraint. And the next steps are to solve the system made by the first partial derivative set equal to 0. And that's very, very easy. And then eliminate between the two equations the undetermined coefficient. And the result is that L1 over L2, surprisingly or coincidentally, turns out to be 2 to the power 1/3. This, of course, empowers you to imagine another drawing like this, where on the abscissa you have another proportion called L1 over L2. And these ticks represent another population of would-be designers attracted by the idea, a group of n size, say 10 or so people with their own ideas. There were 2 degrees of freedom those two proportions. And the net result, if you want to think about shorthand, is expressed as the perfection or the optimum or the configuration for the minimum capital R. So minimum corresponds to d1 over d2 equals, 2 to 1/3, and then L1 over L2 to 1/3. This is for fully developed laminar flow. This result was first discovered by Hess. Hess, a Swiss medical doctor. See, the medical doctors were the ones concerned with the bifurcations of capillary blood vessels and stuff. Hess. And I wrote somewhere here the year when he did it. He published it in 1914. More than 10 years later, Murray, I think he was at Hopkins, but anyway, in the US, in 1926, published basically, some people say generalization of what Hess discovered. And everyone ever since refers to this result, the first one, as Murray's rule. Because it rules the change in diameter at the bifurcations of blood vessels. It's supported by measurements and the rest. So, in my humble opinion, the reason is that Murray published in English and Hess published in German. Yeah. Before you start feeling sorry for Hess that he got robbed, actually he won the Nobel Prize for many things, so everybody was happy. Yeah. But it's known as Murray's rule. This other thing, this is my contribution to this particular story. And, but the implication is a lot more important. It has to do with the fact that the drawing with which I began had 2 degrees of freedom. 2, not 1. Meaning, unlike here, in this drawing, there is only 1 marching on the abscissa to the right. And so the drawing that says it all, I have not made it. I'm making it for you right now, maybe for the first time. Would look like this. You have a performance here called this group proportional to the delta P divided by m dot. And 2 ways to skin the cat, namely d1 over d2 and L1 over L2. We know that coincidentally, the so-called ideal ratio is at 2 to 1/3 and 2 to 1/3, which means that the minimum of this function of 2 variables would be this belly button. So here is that function. It may look like this, and this is the bottom of the bucket, and the value called R minimum would be that. But we also learned that in the vicinity of every, exact result, a crowd of of competitors gathers, a crowd of size n. So here's that crowd. And you can see it embracing this point here. And it's the same the case with the effect of knowing the optimal L1 over 2, another crowd. So I've got n here and n here. And you get the idea. In other words, n times n. Here is a population of competing designs in the vicinity of the best. The size of this population is n squared. N squared is a measure of the diversity. You can think of this blue spot as a cut at minimum plus epsilon, a cut of this bottom. In other words, a projection of this chopped bottom on the base plane. This is the population of people with almost identical claims to perfection. And this epsilon is called imperfection. How are they called it? Not splitting hairs and not painting the lily? Yes?
Shouldn't the diversity projection be a circle if you wanted to say?
I know, but the circle is two-dimensional, and the other name for a very, very cheap circle is the square, or the equilateral triangle, or the regular hexagon. Those are all roundish I call them. That's okay, fine, that's fine. Yeah, that's right. This blue here should be more like this. But the point is that this area has the size n squared. And so the lesson today, meaning if you compare this drawing with one of these, is that from entertaining 1 degree of freedom to 2 means more freedom to change the drawing, leads to not only abundance of high performance, but also never discovered until now, greater diversity. And what is important in this conclusion is the direction of the arrow. And I asked in the first lecture to think whether it is possible to go in the opposite direction, in nature that is, from imposing diversity and arriving at this left end. In other words, confusing the effect with the cause. That's a question to all of you. Until toward the end of the course, you'll see that the answer is pretty obvious. And that answer is no. All right?